Welcome back to The Explainer. So today we're tackling something that's literally at the heart of modern infrastructure. Have you ever deployed a massive application and just kind of wondered exactly how Kubernetes pods ping each other across completely different physical nodes? Honestly, when you see hundreds of containers communicating so seamlessly, it's incredibly tempting to view it as some kind of impenetrable black box magic. But is it really magic? Or is it just a massive, elegantly orchestrated combination of classic Linux kernel technologies? Well, that's exactly what we're going to figure out today. Let's be real for a second and acknowledge right out of the gate that Kubernetes networking often causes massive cognitive overload. Even seasoned engineers sometimes just install a network plugin, cross their fingers, and really just hope it all works. But as focused learners, we don't settle for hoping it works, right? We want to actually understand the system. So we're going to peel back the onion today. We're going to completely demystify this magic trick and show you that beneath the surface, it's a brilliantly logical system that you can absolutely master.
Here's our roadmap for the explainer today. We'll start with the core networking rule, move into same node communication, then tackle cross-node overlay networks, compare pod versus service networking, and finally look ahead at the eBPF era. All right, let's jump right in.
Okay, Section 1, the core networking rule, which means absolutely no NAT required. So before we even start looking at plugins and virtual cables, we've got to establish the absolute law of the land. This right here is the core anchor requirement of Kubernetes design. Every single pod can communicate with every other pod without network address translation, or NAT. What does that actually mean in plain English? Well, it means any pod can directly access another pod's IP address. You don't need complicated port mapping. You don't need an overlay gateway acting as some sort of middleman just for basic visibility. The system assumes a flat network where IP addresses are essentially real and routable right within the cluster. This is the absolute bedrock rule that everything else is built upon. Moving on to Section 2, same node communication, or local pod routing. So how exactly do two pods sitting on the exact same physical machine talk to each other? Well, to answer that, we actually need to bust a pretty major myth first. A pod is not just a simple containerized process running naked on a server. From a networking perspective, a pod is practically a mini Linux machine. When a container runtime, like Containerd or CRIO, creates a pod, it generates a totally dedicated Linux network namespace. This means the pod gets its very own network interface, its own ETH0. It gets its own routing table. It gets its own unique IP address. It is a completely isolated networking bubble. Now, what's really interesting here is how we break out of that isolated bubble. Linux creates what's known as a virtual Ethernet pair, or a VETH pair. You can think of this, quite literally, as a virtual network cable. One end of this virtual cable is plugged directly into the pod's isolated network namespace. That's the ETH0 we were just talking about. And the other end of this cable, it's plugged right into the main host namespace. It's a direct two-way virtual wire perfectly connecting the pod to the server it lives on. But, just having a wire plugged into the host isn't really enough, right? It needs to actually talk to other pods. So the host end of that VETH cable hooks into a Linux bridge. You might see this labeled in your systems as CNI 0, Docker 0, or Flannel 1. This Linux bridge acts exactly like a physical network switch sitting on a desk. It acts as a virtual switch that learns MAC addresses and forwards Ethernet frames between pods. So if pod A wants to talk to pod B on the exact same server, the data travels up the VETH cable, hits the Linux bridge, and gets switched straight down the other VETH cable right to pod B. It's just pure classic Linux networking.
All right, Section 3, cross-node overlay networks, or multi-node routing.
Now here's where things get tricky. What happens when we leave that single server? If Node 1 has a pod with one IP, and Node 2 has a pod with a completely different IP, how does Node 1 physically know where Node 2's specific pod IP address even lives? Here's a crucial little secret. Kubernetes itself doesn't actually do the networking. It doesn't implement the cross-node routing at all. Instead, it defines an interface and delegates all that heavy lifting to a Container Network Interface plugin, or CNI. The true network is built by plugins like Flannel, which is super simple and uses an overlay, or Calico, which is a massive enterprise standard that can use BGP routing and network policies, or Cilium, which represents the absolute newest generation of networking. Honestly, these plugins are the actual traffic cops of the cluster. So the most common way these plugins solve this cross-node puzzle is through what's called a VXLAN overlay network. Let's de-jargon this completely. Imagine pod A on Node 1 wants to send a message to pod B over on Node 2. Node 1 looks at the destination IP and basically realizes, hey, wait a minute, that entire subnet lives over on Node 2. And this brilliantly illustrates the concept of encapsulation. Node 1 takes the original packet with those inner pod IPs and wraps it entirely inside a brand new packet. This outer packet has the physical IP addresses of the real-world nodes. It's exactly like taking a small letter and sealing it inside a larger shipping envelope. This larger envelope travels across your physical office network, and when it arrives at Node 2 opens the outer envelope, decapsulates it, finds the original pod packet inside, and forwards it straight down to pod B. You've essentially laid a virtual network right on top of a physical network. Which brings us to Section 4, Pod versus Service Networking, focusing on networking abstractions. So the crucial point here is that because pods are ephemeral, meaning they die and restart all the time, completely changing their IPs, things can get super confusing. We really have to separate pod networking from service networking. Pod networking is real. It's actual IP to real IP communication using direct point-to-point routing via the bridges and overlays we just explored. Service networking, on the other hand, that's an abstraction. When you query a service, DNS resolves it to a virtual cluster IP. That virtual IP doesn't physically exist on any network interface anywhere. Instead, a component called kubeproxy intercepts traffic destined for that virtual IP using traditional Linux tools like IP tables or IPVS, and it artificially rewrites the destination to point to a real living backend pod. Basically, pod networking gets the data to the machine, while service networking is the load balancing trick that ensures it hits the right active application. Let's move to our final topic, Section 5, the eBPF era, and see how this builds into the future of Kubernetes networks. Okay, before we fully jump into the future, let's just summarize the ultimate takeaway of what we've covered today. Honestly, Kubernetes networking isn't magic at all. It's simply the automated orchestration of a mega combo of core Linux kernel technologies. It's Linux namespaces providing isolation, VETH pairs acting as cables, Linux bridges acting as virtual switches, VXLAN overlays connecting servers, and IP tables handling the routing and load balancing. Kubernetes is literally just automating these classic, time-tested tools. However, here's the catch. As our clusters have grown absolutely massive, those traditional tools, well, they're starting to show their age a bit. Modern Kubernetes networking is actually beginning to abandon traditional CPU-heavy IP tables and complex overlays. Instead, the ecosystem is fully embracing a technology called eBPF, along with smart routing. Plugins like Cilium use eBPF to run secure, sandboxed programs directly within the Linux kernel itself. This bypasses massive amounts of overhead, processes packets up to 10 times faster, and makes routing decisions at absolute lightning speed. We're literally moving from a world where Kubernetes just stitches together separate Linux network tools into a totally new reality where Kubernetes networking is natively fused right into the Linux kernel itself. As Cilium and eBPF push us into this new era, I want to leave you with this one thought. If Kubernetes was able to absolutely conquer the world just by automating basic Linux bridges and iTables, what new limits of performance and security are we going to break when our clusters become fully kernelized? Think about that as you design your next architecture. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you in the next one.